How y'all doing today? Okay, an amount of thumbs up. Anyone have any questions, needs, concerns, etc. before we get started? All right, so we've been talking about rotation. On Monday we talked about centripetal acceleration and centripetal force. I would hope the projector was on, wouldn't it? We've also discussed briefly the ways in which rotation is described, namely how the ways we describe angular motion, angular displacement, angular velocity, angular acceleration, and how all these concepts relate back to the ways that we describe linear motion. Today I want to practice both this and centripetal force a little bit more before we start applying it to some more complicated things. And on Monday we kind of discussed the idea that rotation and linear motion can happen at the same time. So that's the main thing we're going to be looking at today. Scenarios in which both rotational motion and linear motion overlap and correlate with each other. And the place where that most easily happens is just cases where there are wheels rolling along the ground. Because as a rolling object rolls forward, it will displace both linearly and angularly at the same time. So delta x forward, delta theta for how much it has spun since that starting position. And those two things are linked to each other, correct? The number of times the wheel spins is tied directly to how far forward it rolls, correct? If it spins twice as many times, it should roll twice as far forward. Does that make sense? That's going to be one of the things we're demonstrating here with this example. Here we have a car with 4 wheels. The number of wheels doesn't matter, but the size of the wheels does. Car is initially traveling at 29 meters per second forward. That also means that each wheel is rolling, well, also moving forward at the same speed. They're all stuck together. So that is also the initial linear speed of the tires themselves. And eventually this car is going to hit the brakes and undergo a constant negative acceleration of negative 1.75 meters per second squared in order to slow down. Separate from that is the radius of the tires. This is again radius, half of the diameter. And the tires are all 0.33 meters in radius. These are actually pretty big tires. And we have to figure out some details about what's going on based on this information. First question, how quickly are the tires rotating at that initial speed? At the initial linear speed of 29 meters per second, how quickly are the tires spinning while that happens? So the information that we have so far is linear velocity initial, linear acceleration, and tire radius. And the thing that we are being asked for is an initial angular velocity, omega initial. And that might pose something of a problem because all the formulas that have omega in them don't have V or English A in them. Omega equals theta over time, theta equals et cetera, et cetera. There's a theta in this one, but again, that's alpha, not English A. Meanwhile, over here, everything that has velocity and acceleration, it doesn't have delta theta. It appears as though the linear and angular worlds are taking place somewhat separately from each other. So we need to figure out a way to bridge the gap, turn our angular information into linear, and turn our linear information into angular information. So it's time to start using this middle column that I haven't acknowledged up until now. these formulas exist to turn linear data into its angular counterpart. What these formulas say is that the relationship between how far forwards the wheel rolls and how many times it spins depends on the radius of the wheel. I said a second ago that if you're watching a tire roll along the ground, the number of times it spins has an effect on how far forwards it rolls. They're directly correlated, right? Twice as many spins, you should move twice as far forward. So this formula does say that, but it also specifies that the radius of the wheel affects how the two translate to each other. As long as you know the radius of the spinning object, you can turn any of its linear data into angular data. And the radius does matter because it kind of multiplies, literally it multiplies in the equation. To kind of demonstrate, I'm going to take the bike tire and I'm going to compare it to an object with a much smaller radius, namely that golf ball. Parking the golf ball here so it doesn't do that again. I am going to take these two objects and I am going to rotate them by the same amount. I'm going to do one full rotation for each. To start with, we have the bike tire. I'm going to put my hand up here on this piece of metal and I'm just going to spin it around until my hand is in the same position again. So first off, one full rotation here, and that takes the tire to right about here. So that was one full rotation of the tire, 360 degrees or 2 pi radians. Let's now look at the golf ball. I'm going to start at the same position. Note this black line here that we can use to see how far it rotates. I'm just going to spin it until the black line is back on the top. And one full rotation later, and we're done. That was the same displacement, but only angularly. They have the same angular displacement. They both spun the same number of times. But because of their differing radii, the angular displacement was different. And as a result, they also have a different linear speed, and they would have a different linear acceleration because of the differing radii. Basically, bigger objects have to spin fewer times to go as far or as fast, which is one reason why trucks have really big wheels. Alternatively, if you have something with really teeny tiny wheels, like a Hot Wheels car or a wagon, if you ever get those things moving really fast, those wheels are struggling. So, all this to say, as long as you know the radius of the object, you can turn linear into angular. And since we know the radius of this car's tires, we can turn VI directly into omega I, as per that middle formula there in that column. So those three equations are called translation or transformation formulas, specifically because their entire purpose is just to turn one into the other. And they have their own column right here on the formula sheet. Again, directly between the linear and angular stuff, so outlined the same way as they are over here. Excuse me. So we can use this middle one to turn P into omega. Questions about any of that? All right. So the initial is going to equal R times omega initial. Therefore, 29 equals 0.33 times our unknown. Set unknown, if memory serves, should come out to about 87.88 radians per second. disagree? So that is the initial angular speed of the wheels. And radians per second does tell us basically the same thing as like degrees per second or rotations per second. It's just a different specific unit. Next question though, I would like to actually take this and turn it into the similar unit of rotations per minute, just to see how it compares to that other unit. So this is a unit conversion. And rotations per minute is a slightly more common unit for this sort of thing, at least in the United States, because technically all cars should have an RPM meter that tells you the rotation of the parts of the car. So we're just going to turn this into rotations per minute to compare, build up the frame of reference. This number is in units of radians per second. We have to turn radians into rotations and seconds into minutes. These are the two conversions that you will occasionally need when dealing with rotation stuff. One full rotation is equal to 2 pi radians, which in turn is equal to 360 degrees. I would encourage you to write that on your formula sheet. It's something that I would tell you on a test, but it saves you time if you already have it. So, we're going to turn the radians part of this into rotations so that it's in terms of how many times it spins per second or per minute instead of just radians, which even I, after doing physics professionally for 10 years, I still have a hard time thinking in radians. Sometimes I have to turn it back into rotations just to show so my brain better wraps my... I'm trying to talk and it's not going well today, excuse me. Sometimes even I have trouble with radians and I turn it into rotations to make more sense of it. So I'm just going to treat this like any old conversion. We've got rads per second, and I'm going to multiply it by a fraction to cancel out radians and replace it with rotations. So this would be 1 rotation over 2 pi radians. I usually abbreviate rotations to ROT. I do appreciate that ROT and rad aren't that dissimilar, so I'll try to say rotation out loud. 1 rotation over 2 pi radians. This is so that this radians cancels out with this one's and leaves us with rotations per second. We can work this through just to figure out the number of times per second it spins, which, again, just for context's sake, that's about 14 times per second, which is pretty quick. But we also want to turn seconds into minutes, so I'll just tack on 1 extra part. Seconds is down here, so I'm going to put 60 seconds, that's the top part of the fraction, and 1 minute on the bottom. And all of that multiplication should give you about 840 RPM. Did anyone get about 8,000 RPM? All right, that is a mistake that your calculator is making that I want to address. You didn't do anything wrong, your calculator is just being dumb, because secretly all machines are dumb. Don't tell them I said that. The issue there is, namely this part, the dividing by 2 pi. Because if you input this into your calculator, number divided by 2 pi, again, machines are real stupid. what it's going to do is it's going to divide by 2 and then multiply the answer by pi. And so rather than divide by pi, you multiply by it, which technically means your answer is times pi squared bigger than it's supposed to be, which is, 3.14 times 3.14 is about 10. So that's why it's 8,000. To fix this, you could just put a parentheses enclosing the 2 pi, and that should do it. So, once again, I'll say it till the heat death of the universe. Just be very careful with your calculator and make sure you understand how it thinks. It's not right, it's just you need to know how to use the tool. So that's where the approximately 840 comes from. If you've ever looked at the RPM meter in a car, you'd see that it usually has pretty big numbers on it. It goes from like 0 to 8,000. So big numbers make sense here. Any questions on this part? All right. I'm gonna erase this to make some space. Next question. How many radians does each tire rotate through before the car stops? So at this point, we're going to hit the brakes, apply this negative acceleration, and we're going to bring the vehicle to a complete stop, which would mean that VF and omega F are both 0. So that's free information. And what we're after now is delta theta. We want to know how many times the wheels spin as this deceleration happens. So, what options come to mind, given what we know and what we want? There is kind of a weird, there's a problem that we encounter working through this one, because our goal is to get to delta theta. And on the way there, this is the list of things that we have. Some of it's linear, some of it's rotational. If we look at the formulas that have delta theta in them, we start running into a few problems. One, we don't have time, like at all. So if a formula has T in it, it's probably not a good idea to try right now. Furthermore, this formula is doubly not good because it inherits the same problem as this one. Namely, it doesn't work if you're accelerating. So that's true for both of these. The wheel is definitely accelerating, so these two are just out by default, even if we knew what T was. But since we don't have time, that kind of eliminates formula 3 as well. But formula 4 does pretty well describe what's happening here. The wheel is rotating some number of times while it accelerates and changes speed. And this correlates to how, when you hit the brake in the car and decelerate, change speed, you will slide physically forwards while that happens, right? Like, the car doesn't magically stop, it skids forward while you slow down. So this delta x, bless you, correlates to this delta theta. Like, they represent a similar thing, it's just the wheel spins as it slows down, like how the truck slides forward while it slows down. The issue is, this is a good formula. It talks about the acceleration. It doesn't have a T in it. The problem is that we don't have alpha. We know linear A, but not alpha. Now, we know linear A, which means we can figure out delta x, but that's not delta theta. So we actually have two decent options here, but each one is missing something. And to get where we want to go, we have to convert again. There's at least two paths to get to the answer here, as there often is in this class. This formula would allow us to solve for delta x and then turn delta x into delta theta, or alternatively, we could turn out acceleration into alpha and use this formula instead. So one way or the other, we have to convert something and then the order's mixed up. But either direction, there's a conversion and a use of Formula 4. And both should get you to the same place. It's just kind of a question of, do you want to convert first and then use the formula, or use the formula and then convert? And that's going to kind of be a running theme in these rotation questions. Often you could do it entirely linearly and then convert to the rotational stuff, or do it rotationally and convert back to linear. So there's usually multiple options on how to proceed. I'm going to show both just to prove that they work. First up, I'm going to show the rotational method. I'm going to use angular formula for omega final squared equals omega initial squared plus 2 alpha delta theta. We want delta theta. We do know the change in angular speed already, so we just need to figure out alpha. And conveniently, we are able to turn A directly into alpha with one of those middle formulas. Negative 1.75 is going to equal 0.33 times alpha. Alpha, memory serves, should be about negative 5.303. And the units on that are rad per second squared. It's the same as normal acceleration, but with radians instead of meters. This represents the rate of change of the wheel's rotation over time. And with that alpha found, we can now use this formula correctly. Omega final is 0. Thankfully, 0 squared is still 0. Omega initial is 87.88, and that needs to be squared. Make sure that you are only squaring the 87.88. Plus 2 times negative 5.303, and solve for delta theta. They would disagree with about 730 radians. All right. Just for context building, that would be about 116 rotations if you divide it by 2 pi. So they spin 116 times on the goal of slowing down. So, for that method, we converted our stuff into angular and then used the angular formula to get what we wanted. I will demonstrate that the alternative tactic also works, solving it linearly and then turning it into the angular stuff. So, the linear version of Formula 4 would be still 0 squared, but that would instead be equal to 29 squared plus 2 times negative 1.75 times delta x. Delta x turns out to be, I think it's 240. Yeah. This means that the truck is going to slide about 240 meters forwards as it slows down. And delta x equals radius times delta theta. 240 equals radius times delta theta. And delta theta, once again, turns to be about about 730 again. Just some slight differences from rounding. So once again, either method works. You can do it linearly and convert. You could do it you could convert first and then do it angularly. The two linear and angular worlds are both intrinsically connected as long as the object is doing both at the same time. How you guys feel? Mixed responses, fair enough. Any questions or concerns for right now? All right. Well, the last thing I really want to do today is get in a little bit more practice for the centripetal force stuff we talked about on Monday, because lab is about that this week if you haven't had lab yet, and Friday is going to continue to involve it. We're going to go back to centripetal force for a day and look at how the gravity from Earth acts on the moon, more specifically in that case. So we're going to do another centripetal force example real quick as our last thing of today. Specifically, the centripetal force is involved on a fighter jet and the pilot in a fighter jet. Have you ever heard, through either science documentaries or even in movies, that centripetal force is dangerous for pilots who are turning jets very quickly, and that they might perhaps be rendered unconscious by it? That's kind of what we're dealing with here. We have a 2,000 kilogram fighter jet flying at Mach 2. Mach 2 just means twice the speed of sound. In metric, the speed of sound is 343 meters per second. So Mach 2, twice that, is 686 meters per second. So this is likely one of those show jets that flies overhead, makes a sonic boom, and annoys people. And this pilot is going to have to turn the jet at speed. So this will be its constant speed throughout the entire turn. The way that turning works for aircraft, since you don't really have wheels that you can tilt, is the plane just has to tilt its entire body and a few of its other, I almost said a rudder. I guess I don't know the technical term for the flaps that move one way or the other on a plane. The jet equivalent of a rudder. And when you physically turn the plane like that, you change the direction of the thrust forces acting on it, basically redirecting some of the forward thrust to the side. And so the plane basically generates its own centripetal force by banking. And once the centripetal force starts acting, it's kind of like there's an imaginary leash that physically forces the jet to start turning as long as it stays banked at that angle. So if you've ever watched like Top Gun or something, you physically see the jet bank and then it enters the turn. So the banking just refers to the tilting like this. While banked, it generates that centripetal force. It starts moving around the edge of a giant invisible circle, rotating about some central point in the middle. And the radius of this giant circle is referred to as the turning radius, which same thing is also true for cars, if you've dealt with turning radius in any context before. So, very fast plane, turning, there's going to be a lot of centripetal force causing it to turn over a very large turning radius. Now, bless you, the jet could probably turn a lot faster if it was being operated by a robot, but instead it's being operated by a human, and humans are full of blood, usually. And kind of like what I mentioned on Monday, the blood can kind of be considered a separate object from the rest of your body, meaning that, bless you, when the human starts turning, the blood is going to try to rush to one side of you, like how in a centrifuge particulates go to the edge of the test tube. Basically, this pilot is centrifuging themselves. And when that happens to a human, the blood rushes usually out of your head into your feet, and if there's no blood in your head, you aren't awake anymore. I believe about 10 G's worth of acceleration is enough to knock most people out. Some people have gone up to 15 G's in astronaut training. It's not a good idea, but they've done it. 15 G's means that the person in question is accelerating at 15 times the rate of gravity. So 15 times 9.8 to create 147 meters per second squared, which is a lot. If anyone ever talks about number of G's or G forces, this is what they mean. It's just an acceleration equal to blank number times 9.8. Number of times stronger than gravity. And pilots undergo a lot of G-force. They're trained to do it, but even then you still shouldn't go above certain thresholds because the human body can only handle so much. This pilot is being very daring and going to shoot for 15 G's, meaning that they can handle a maximum acceleration, maximum centripetal acceleration, of 147 meters per second squared. With all that information said, and given the two formulas we have for centripetal force and centripetal acceleration, I would like you guys to tell me, first, what is the turning radius of the jet as it turns at that speed with that acceleration? And two, how much centripetal force is required to make this jet turn like this? Give you guys a couple minutes to work on that on your own or with your classmates.
.66
For what?
radius. R.
Not exactly.
I did the same thing, but I forgot to square 686.
Oh, okay. That might explain it. Yeah, so, first question, what would the turning radius be? I would look at this formula, since it has the R in it. So, the 147 represents the max centripetal acceleration the pilot can handle, 686 squared over R. You would want to make sure to square the 686. R should be then equal to squared, 686 squared over 147, and that should be at least 3,200 meters. Which means this jet has a turning radius of 3 kilometers. Jets need big turning radii. And it's why, if you've ever been to an air show, it's why the jets are not always directly overhead most of the time. They get into position to do their trick, they zoom overhead, and then they need, several country miles to get into position for the next trick. So, if you think your car has a bad turning radius, it only gets worse the faster you go. So, huge turning radius when you're going this fast. It takes a lot of space and a lot of force to make a fast object turn. And also, actually jumping off from that, it takes a lot of force to make something turn. So how much force is required to bank this jet?
294,000 kilograms per something.
Yep. Force centripetal equals mass times acceleration centripetal. So the 2,000 kilogram mass of the jet times the maximum human withstandable 147 meters per second squared gives us approximately 294,000, that's 1 newtons. For a sense of scale, that is about 66,000 pounds or 33 tons of force. Now, not all of that is acting on the human themselves. This is the force acting on the metal of the jet. But the metal of the jet needs to be able to withstand this much force, lest the wings tear off mid-flight. That's why not every plane is a jet that's designed to go supersonic. It's also why, well, to reduce that force, planes tend to take turns slower and over greater distances, because less speed and a bigger distance reduces the centripetal acceleration requirement, and so most passenger jets have very big turning radii and go comparatively slowly. Most passenger jets go nowhere near the speed of sound. If you've ever been on a passenger plane, flying into or out of an airport, you probably noticed that in the time it took you to bank in the correct direction and actually leave the airport, you were probably several miles and city blocks away from the airport itself. Because again, gigantic turning radius. Questions? All right. That's pretty much it for today. I'll at least set up an expectation for what we're going to be looking at on Friday before we break. One of the places we talked about centripetal force acting was the gravity from the Earth causing the moon to move centripetally around the planet. This happens because of the force of gravity between the two masses of the two objects, but really this happens again because of gravity for anything orbiting anything else in space. So there's almost an entire branch of science just dedicated to using gravity in this example to look at how space objects centripetally accelerate around other space objects. Because in space, most things tend to orbit some other thing. Even our own sun orbits something else at the center of the galaxy. And so Friday, we're going to be investigating that. Namely, we're going to be investigating how to calculate the force of gravity between two planets like this. Because 9.8 doesn't cut it when the two objects are this far apart. When you are this far apart from Earth, the moon's acceleration from gravity isn't 9.8 anymore. So we're going to cover a new way to calculate gravity such that it can be used in situations like this. So Friday will be about space physics for the most part, and then next week we will look more at different applications of terrestrial rotation like torque and stuff. Questions before we break? All right, work on your homework, let me know if you need anything, bring all these notes to lab, and have a great day.